and I'm working on the ice. And many of you are asking about what is something that you worth the while for the ice. Professor, no, what are you doing? I said, I'm working on water. So what are you doing with water? But if you study about this article in 2008, you'll be very surprised that nobody understands actually the water, and this is the tagline. And the second one is that we feel a little bit shy, we feel a little bit shame because water takes about 2/3 of the world, and we don't understand at all. And the third thing is, what is even worse, that the more you study water, the more problems is discovered. So it doesn't mean that for the general research you reduce the questions, but more questions arise when you study more on water. And this is an issue. Regardless whatever you say, people say that, we lack of all the resources in water, but we are unable to have a water shortage. We can have a short of food, but not water. Water is the worst. And personally, I feel that water could have been also for China is going to be an opportunity because Europe doesn't have water, and U.S. of course in California, but it is even much better for China, and a country like China is really short of water. If we put the energy on water study, this is the most valuable. Not only do we need to do it, in reality, people can understand water, and then people can get kind of Nobel. Once you can also turn on the hydrogen and oxygen, and it's everywhere. So why you do it? So the water is really worth the while for the study. Maybe I'm a little bit too exaggerate, but I'd like to show you a picture. I don't know where it comes from, but this is on the 100th anniversary on the cover on the Physics Association. But why are you looking at this cover? This is on a centenary anniversary. This is a cover. At that time, people are skiing on the ice skating, and nobody asked the question that why you have to ski instead of on the land. The first answer is Ferrari. About 150 years ago, Ferrari said possibly there might be a very, very quasi-liquid layer on the ice surface. This is the first time mentioned about Ferrari. This is not solid on the ice surface, but a quasi-liquid. Why liquid then? People are saying that the simplest two mature argument is that would there be a pressure if you stand on the pressure and then on the ice, then the pressure melts. So you have also a frictional heating, and then you melt the ice. These are the two simple theory. People are thinking about whether these are only the two theories, trying to eliminate. If you add 460 atmosphere and you can increase the temperature of approximately 3.5 centigrades. But we experiment, but in reality, of the minus 35 degrees, you can still glide on the ice with of 75 kilos standing on the ice is unable to skid on the ice because of the minus 35 degrees. So first of all, the pressure is incorrect. And secondly, we have the experience when you stay upward, you still feel slippery. So where does the friction come from? So this is not these two main reasons. So what exactly is? People are doing experiments, and we found it's quite difficult to do the experiment if you want to study. There must be an approach to contact. Once you have a contact, the ice is a kind of light chain. Once you break, for STM, AFM, to measure the melting layer, in reality you are already breaking the original thickness. You are not having the actual value. So what is the difference of the experiments with 272K? It is approximately 10 to 100 nanometer. So there's no way for you to do it. So what about theoretically results? and it's even 2 or 3 orders than the experiment. So such data is unable to believe in physics. People are thinking about why this is a situation, and the first thing, what exactly is ice? What we call ice, which is quite simple. About in 1933, people telling you what exactly is the ice. You can fulfill 2 conditions. One is that every oxygen atom has 2 OH bonds. As you can see in the middle, 1 oxygen, and it forms also with the water to have OH bonds, and another OH bond with another. And this is the 2 hydrogen, quite interesting. Secondly, every 2 hydrogen atom between each 2 nearest will be oxygen atoms. Then this is also will have unlimited phase, and people are looking at the new things, so it's unable to tell. If you look at 1 oxygen atom or a water molecule, which is a very complete crystal without any kind of a default, I'm just showing you also the oxygen atom without any disorder. But if you put the hydrogen, you see a lot of way on the little white dots everywhere. You call it a proton disorder solid. In other words, once you put in the oxygen, you turns worse, and this is ice. Once oxygen comes, it becomes very complicated. So you don't have to study on oxygen, but once you put in the hydrogen for the bonds, you have a lot of scenario. Now, then a lot of tricks. For example, one of which is that generally speaking, when we look at the ice, which is of ice, IH, on the proton disorder, but if you turn down the temperature less than 72 K, temperature change, and the proton will become ordered. This is a famous kind of bulk from disorder to the order change. This is a mature case, and I told one of my students that, well, this is quite interesting, and so you have the bulk ice change, and why don't we there'll be any kind of a transition on the ice surface. So would that be on the surface of ice? There might be a transition like that. So I was trying to simulate the case. So when I started doing it, and that was good. Dr. Pan, and he's quite smart, and I don't want to repeat the details. When first of all, we make some calculation on the cohesive energy on the bulk ice, and talking about on the relevant ordered array with the protons array, and take a look of also the cohesive energy, what will be the difference, and making so many calculations with summarized within this bracket with different kind of protons placement, and the energy difference is only about 5 to 6 MeV versus the 1 single H2O, very, very minimum. And you have a very, very flat line with the cohesive energy. So how do we place the hydrogen? And it doesn't affect too much. So in the very beginning, we're quite disappointed. But if you talk about, you have to make a calculation of the surface energy. And when you make the surface energy on the same table, so we was quite shocked, the change of which is so big that once you have a different proton, the surface energy is entirely different. Or we've been thinking about what exactly is for this kind of cohesive energies on the hydrogen, what will be, which is about 6 MeV, but for the surface energy, it can be more than 100 MeV. Then we don't know why hydrogen is having a different position on the surface, and the surface structure is so big. This is number one challenge. And then we've been thinking about which surface should we start. And the student was quite, Dr. Pan is a very, very smart student. It's an individual. She's been thinking about, give me a surface, and I'll give him a title. For example, give a name to a newborn baby. And this is way that she does it. Okay, I thought about a naming rule. This is what we call the order parameter. And this is what he has done. So if a specific service facing, which is also a kind of a hexagonal face with the number to have it summarized with all of the data. And in the hydrogen in the center, you have 1, 2, 3 bonds, Ci equals 3, with all the service offering each of them to summarized and having this kind of bond, so have it divided, and the value is less than 6. In other, this is an order parameter. This is a continuous value. And once you have the order parameter, I did not feel that, well, at the end of the day, there has to be a kind of a data like that. So when we check on that, the most random proton with 3, gradually it is quite evenly distributed with the hydrogen evenly distributed, and if it's equals 2, it is quite in good order. If it's close to 6, it means that this little white box will be focused in one corner and the rest will be in red. So the larger the number, the homogeneous on the surface. So there will be separate sectors of the white and the red dots. And the random is approximately 3. So from this formula equation, you can say, and you can give a name, I can check what kind of parameter it is. And this is the way it was thought. So there will be only 2 only, which is a very ordered service. And then I'm saying that now that you can name it, and on the, can you also make the surface energy with the axis y together with the surface energy, and then you come up to this kind of dotted line. With this kind of random, it turns out to be a kind of standard line, and each of the spots, the error bar is not to be larger, and we have to make sure that, so we calculate on different issues.
So for the first point, on the very random service, this is the maximum that we calculated with the computer. You can see the red dots and white dots. And for the random surface, the surface energy is not the lowest. What is it? For the ordered surface, the surface energy is the lowest. So that brings to a question. The more ordered the surface of the ice is, the more stable it is. So Mr. Xie just left. He is very interested in this. For the semiconductor surface, you can cut part and relax the surface, and you get the surface. But for ice is different. If you put your hands on the surface, it becomes the best surface. So how do we understand this curve? It takes us a very long time. But later we found that it's very simple. We can use the electrostratal dynamics to understand it. There are 2 parts of the surface energy. One, the order surface plus delta. So that becomes the disorderly surface. The curve starts from this, and this point is the most orderly, and we add a delta and a delta, so it becomes increasingly disorderly. So how do we increase the delta? We found the interactions between the protons on the surface is not the order proton. It is the dipole, meaning effective electron. We found that it's 0.2 electron. We found if the protons are interacting with each other on the surface, we would not use the electron to describe it. We use instead the dipole to describe it. So that is equivalent to the interaction between the effective electron charges. So we rewrite this formula like this, and we can draw a curve like this. This is the formula. So after the curve is established, you can see it is close to the complicated curve generated by very complicated mathematics. When we are calculating, it takes us over 1 year to draw this curve, but with the calculator, it takes us only 10 minutes to finish. So at that time, I was very much surprised. But we know the physics dynamics is like we cannot use electron interaction to describe it, and instead we should use a dipole to describe it. And this is physics. It's nothing but this. So we would like to answer this question. On the surface, it is necessary to have the phase transition from disorder to order. Before that, the Australian team has done a research to study the difference between the temperature in the bulk and in the surface with the phase transition from order to disorder. We found it's not correct because it doesn't use the interaction between dipole and dipoles. It uses the interaction between the electron charges. Another point is very simple. If we use the proton, the single OH bond, we can see we can use the EC model to interpret it, and on the triangular model we can interpret it. But before, Vina told you that we don't have the phase transition like this. There is no big change here. So no matter how we increase this model, the result will not be changed. In other words, there is no change on the surface, namely no phase transition. But we want to find out more answers, so we use a computer to do a Monte Carlo simulation. The condition is very extreme. No matter how you increase the temperature, we keep the oxygen atom on the lattice, no change. We're only looking at the hydrogen. We exchange a little bit. As you can see, this is the surface from 40K to 500K. It is very orderly, close to 2. And when the ice is melting, the hydrogen atom prefer to be orderly. So there is no order to disorder transition at the ice surface at any relevant temperature. This is very interesting.